Okay, it's just gone 8 o'clock. Let's make a start. So today we'll be looking at data processing. And what I would like to say is I know a lot of you might think you're a theorist. Okay, at this point in your life, you typically have a romantic notion of what physics is like. You get to study black holes, you get to study quantum mechanics, etc. What I will say is many more discoveries have been made doing experiments than they have been made theoretically. And so learning how to analyze data, how to construct an experiment and learning how to analyze data is actually a much more useful thing compared to trying to dream up theories which may or may not be consistent with reality. So tonight we have Dr. Andy French, and he'll be talking about data processing as applied specifically to rocketry. Go ahead.
Well, we're going to garnish it with a bit of rocket science, everybody. Good evening. Welcome to the BFO Computational Challenge. I'm Dr. Andrew French from Winchester College. Welcome all. We've got 140 people. Fantastic. Resources will be put on the usual place. If you're new, thank you very much for coming. So, in fact, black holes, just to take up on that, aren't actually just theory anymore because, of course, with the LIGO system, we can detect the ripples in the gravitational fields, the gravitational radiation from colliding black holes. We can detect it directly. And I think they're called standard sirens, I think. So actually that not only allows you to infer experimental parameters of the black holes, like their masses, but also how far away they are. So from the kind of loudness of the gravitational ripples which appear on Earth compared to what they would be at the black hole. So even exotic objects like this, we can use direct measurement to infer information about. So this is about using computers and using software and code and all that kind of stuff, and how we might sort of process data that we measure. Before we kind of get into it, I thought I'm going to dip into some experiments that I'm doing right now. I think it's always important for teachers, if you can, to sort of engage in some new stuff. It keeps things fresh. So I've got a little rocketry project with some of my students at Winchester. So I thought I'd start with a little video that we made. So a bit of sort of tales of misadventure. So this is the nose cone test. Here's one. So hopefully you can see a tiny little rocket. We actually 3D printed a nose cone. This is the sort of Mark 1, where the nose cone was quite light, but we didn't have an attachment mechanism. So this is filmed at very slow motion, and as it comes down, you should see the nose cone detaching. So this is a bottle rocket, a little sort of 1 litre lemonade bottle. There it's coming down now. We had, there we go, that's the full speed. The nose cone just about survived. And this is the another test with a slightly heavier nose cone. You can see it doesn't go up very high. And unfortunately, our deployment system didn't quite work to plan, but never mind. So we used a little clinometer. So it's a little device which you point at the apogee and you press a button and it then measures the angle. And if you know how little distance away from the launch site, about 70 meters in our case, you can work out with some trig how high the rocket went. It was about 25 meters. And for one more, this is a flame trench, which the kids built out of wood. And we rather sort of dangerously put a mobile phone in harm's way. So there we go. That's the water coming out. So experiments can be quite fun, particularly when the weather's nice. And what we'll do is we'll kind of come back to this. We were measuring this in a laboratory. So if I just show the other little photograph here. So what we've got is this is the rig. So we've got a bottle rocket. The fins there are when you attach when you launch it to keep it nice and stable. But the rocket itself, we've got in this sort of rig. It's like the biggest retort stand, the biggest, oldest retort stand we could find. And we've securely clamped it with these little rings here. And what we do is we pump up the rocket. The sort of yellow cable attaches to a foot pump. And I think we've got about 300 ml of water in here. The water eventually, when the valve fails at about 4 atmospheres, the water is ejected in this sort of tube. And underneath is a large black dustbin to prevent the water going everywhere. And what happens, we've got a kind of seesaw device. So the rocket pushes against the seesaw and then pushes down on this pressure sensor. Well, it's a kind of force sensor. And we can measure it 1,000 times a second. If you look carefully, there's a little white box, which is a USB data logger from a company called Pasco. So some of you will see this in your science labs. And this is my laptop, which is recording So we're measuring thrust versus time. And what we're trying to work out is a model of how thrust versus time works for our rocket. Because this is something that happens very quickly. I think it removes the water in about 0.2 of a second. So having 1,000 data points a second at least gives us a fair idea of how thrust versus time will work. And from that, we can build a mathematical model of the rocket, which is a work in progress. Now, here's a question for you. Why have I got a mechanical disadvantage here? Have a look at what I'm circling at the moment. Why is the rocket closer to the pivot than my force sensor? I don't know if you can put a sensible answer. Why have I done this? Okay, so I've got increases accuracy. What else have we got? Let's have a look. I'll give you a few more seconds. Yes, we indeed will take a moment to consider this problem. So why have I got a sensor? Well, why am I not firing directly on the force sensor? If you push down on that sort of white thing, it pushes down and we record the force. So yes, we have less turning moments. Why do you think I've done that? Right, what sort of answers have we got, Nina?
Yeah, we have less moment, reduce percentage error, reduce the risk of damaging.
Yes, so James C is correct. So the force is less, so it doesn't break the sensor. Indeed, what you can't see is it says 50 newtons maximum written on this. And it's probably, I'll get into lots of trouble if I break these sensors. I think they're quite expensive. So, so what we've got, the force on here times this distance here is the thrust just about times this distance here. So it's actually a factor of 2, I think. So whatever we measure with the force sensor, we have to double it to get the actual sort of thrust of the rocket. And actually it's slightly more than 50 newtons. So so we're looking at about sort of 100 to 110 newtons of thrust is the maximum thrust from our rocket. So there we go. You have to kind of work with what you've got. And also, having it directly on the sensor can have problems. We did our first sensor. I think I might have to, I don't think I've got this video to hand, but we launched it outside. There's a sort of a quad you can see through these rather dirty looking windows. We launched the rocket without all these little rings. And the rocket disappeared for about 3 months. And we ended up in a tree of one of my friends in his house. So it basically escaped. So there we go. You can have all sorts of fun with experiments. Anyway, the purpose here is we're saying, okay, how can we investigate the real world, have a direct encounter with reality, which is kind of what I think science is about, and use the tools to kind of make measurements that the human eye and the pencil can't do. So in this case, we can't really model at all, can't measure, should I say, what's happening on timescales less than a second. So we're having to measure things 1,000 times a second, and then with a sort of rig here, which we can do in a lab, and that gives us about some information about a process which happens too fast for us to measure. And we'll look at a few of those kind of things today. A variety of things that you can do slowly, statically, and things which are dynamic. So what we're going to have a look at is just a couple of examples. If I go back to the presentation, this is what you can download from the Eclecticon. And we'll start off with this. And it's going to look at a sort of idea of going from Excel to a programming language. Obviously, anything, you can use anything you like, but something which is not just Excel. And sometimes when you're doing things in Excel, what happens next is quite a complicated recipe that you would like to repeat. And so it's often worth, if your opportunity cost is not too high, to create your own code. All right, so make a pipeline of data processing. And if you ever find yourself getting involved with a kind of professional or perhaps a university project where you're measuring things and you've got a big experiment, that's the really fun end of science. Maybe you spend years creating this for maybe a small couple of seconds when you do your experiment. And you think about, the rocket launches from tests from SpaceX at the moment and others, the work that has gone into all that instrumentation is a fabulous, sort of example of practical science. Some of you may be getting involved with that in future years. So if you have a look at some of the boxes I've got here, we've got some raw data in Excel. And I'm going to use a very simple example involving pendulums, plus a few other bits of kit. And then we'll have some sort of ingest box. Now, pretty much every time I've done an experiment, and this is at school and then in my previous career as an engineer, every single time I had to write an importer. So in other words, to liaise with the system that's creating my data, recording my data, and how I can make use of it myself. This is something that you will just find. And there are no good standards for this. There's always something unique. So knowing how to move data from one form to the other is a really useful skill and will make you employable, definitely. And then there's the fun stuff, doing the maths. So in this particular case, we've got some averages, plotting graphs, lines of best fit, all that kind of stuff. And then we might have some representation. All right. So this is about turning data into information. So, and I think rather than talk about it, well, let's just see some examples. So here we go. So here's some data that you could take yourself with a pendulum. So a piece of string with a bob. And I think I've been naughty and used an actual simulation for this, but obviously please do it yourself. I'm going to show you some example with slinkies, which you can do at home very cheaply, and maybe with a ruler as well, and some masses if you've got access to that. So if you can have a look at the spreadsheet. So if I'm actually doing stuff in the lab, which is, I might be measuring the period of a pendulum, for example. Let's just say I'm measuring 10 periods and I vary the length of my pendulum, right? Say between 10 centimeters and a meter. And, I might want to write that directly in Excel, something like this. But this is okay. But ideally, what you want to do is have some system which you can plot as you go. So if I've got that as a, so I think what I'll do actually, before we get into this pipeline, I'll show you an example where we have got something that plots as we go. So if I just come out of this, I've got a few examples here. So I think we'll look at this one. Here's my cantilever. I just want to check if I've got the right graph here. Yeah, there we go. So this is a cantilever. I hope that's nice and clear. So that is a Mark 1 meter ruler that you can find in pretty much every physics laboratory in the world, made of wood. And maybe you might want to ask permission if you do this experiment. It does bend it, but it does go back. You don't really want to go much more than about a kilogram. I've got a pretty fearsome G-clamp here. It's clamping it to the desk. And what we're trying to work out is the deflection of my cantilever. And it turns out the deflection is interestingly related to the cube of the original length of my piece of wood. So I think if you're going to do a physics experiment, you want an interesting law that's not linear. All right, that's that kind of nice test, I think. I'll talk about what the other parameters are in a moment. So let's just have a little look at the setup so you've got some context. And also notice how I'm writing this up. Taking photographs and using, annotating photographs is something that's brilliant with modern technology. Phones and laptops that can take pictures are really cheap. They're everywhere now. And you can use them for good science purpose. So I'm always taking short videos and little photographs of my kit and things like sort of standard measurements. Obviously, you want to write these in a textbook and an exercise book. I can capture that it was exactly 27.75 millimeters wide from this picture. All right, so there we go. So they've got some counterweights and G-clamp. And I'm measuring the deflection of the endpoint. That's what my delta is, using a ruler connected via a retort stand. All right, so everything's all set up and nice and visualized here. So a photograph combined with some notes, that's now something you could stick in a report. All right, okay, so here we go. So this is my lab with some famous physicists on the wall. And there we go. This is what we mean. So this is the deflection. And of course, any parameter that you define in physics, you want to describe in a diagram. This is a kind of biblical rule of physics. All right. And in this case, we actually have a photograph which we can use. So it's really obvious what your parameters are. So in this case, so my deflection is the end of my cantilever. Right. What is that from the kind of horizontal, the unweighted situation? And I can measure that with my ruler by getting nice and low and avoiding parallax error, etc. And of course, that is the original length. So I've got deflection and length defined. And then I can use this sort of ruler to go along and, really get your eye in. So this is how you could, from almost to the nearest millimeter, I reckon, you can work out the deflection. Okay, so there we go. So that's what we're going to do. And this is the mass, of course, of the ruler. It turns out to be 114 grams. All right, and the length and the width of and the thickness of the ruler are these parameters. That's L, W, and T. All right, so we can use those with a digital caliper. And I've got some quite nice ones in our lab, although they're not that expensive. You can measure quite easily something to 100th of a millimeter. More precision than that probably gets quite expensive. But for schools, I think this is perfectly good enough. So a boring experiment, which I think we'll just sort of gloss over, is the if I vary the load, what's my deflection? And you might be sort of unsurprised that that's linear with the mass. All right, so that's pretty boring. So the deflection goes as the mass. But what's interesting is this one. So this is what I would set up in advance. So if given this experiment, there's nothing's happening very fast. You're loading my cantilever. You're sticking a mass at the end, making sure it doesn't drop on your foot. All right, and it's all safe. And you'd set up a spreadsheet. So maybe you've done a pilot experiment to say, well, what kind of deflections am I likely to get? What kind of loads are sensible? So in this case, I've done the previous experiment and I've gone up to about 1 kilogram, and I get a sort of deflection of about 15 centimeters. And I think, that looks like that's going to break the ruler if I do any more. So I think that's going to be it. So if I fix a 1 kilogram deflection and then move it, move my length of the ruler, and I sort of shorten it. So I'm not moving the mass, I'm moving the length of the ruler from the G clamp, and then I can measure the deflection as a result. So there we go. And I've now got a table where I can directly put in my numbers. And you can use things like color. So, the measurements are here. So you're going to type in those, literally the ones you have from your ruler, and then your computer will calculate those directly for you. So it's worth, I always think, setting these things up in advance, and also getting graphs which plot themselves. And I know a lot of you will go, oh no, this is what my physics teacher's been banging on about for ages. Well, to make it fun, spend a bit of time creating an Excel sheet. And then as you take those data points, their points will appear in your graph. All right. And we can also underlay it with a model curve, but you'll need to measure some other parameters first before you do this. So there we go. So this is what I've done, the green bits. I've measured the length and I've got my deflection in meters. So the model of this, so in physics, we're trying to predict what the deflection is. And if you look at the Graham Wohn's amazing book, The Cambridge Handbook of Physics Formulae, should be on your desk. It's brilliant. The deflection of a sort of elastic beam goes as the cube of its length. That's assuming it's weighted right at the end. So that's the mass of the beam. That's the strength of gravity. This is the width. That's the thickness. And this is something called the Young's modulus. Could some of you tell me what a Young's modulus is, please, in the chat? Yes, that was super quick. Brilliant. Stress over strain. Awesome. So stress has units of pressure. It's the force per unit area. We can think about that as going through a solid, and strain's the fractional extension, the extension over the original length. So that's quite a useful thing to work out. And it's actually quite a high number for things like wood. All right. So this is a good experiment to measuring something that's really quite massive. And so what you do is if you plot, so what we're trying to do in physics is that basically get a straight line graph. This is our main analysis tool. So if we plot the deflection, here we are in the spreadsheet, versus L cubed, if we get a straight line, we can say, well, I think our model is well correlated with our observations. So let's have a look. So, just a point. So the mass of the ruler, the weights you put on it. So in this case, we are kind of ignoring the mass of the ruler. Yes, we'll have to sort of take that into account somewhat. All right, but there we go. So I think the mass of the ruler is not enormous. It will vary a little bit if you've just got the ruler itself, but that doesn't really bend very much. So and what I'm doing is I'm doing the deflection versus no load. So if you like, if you look carefully on here, so we've got the deflection of the ruler with no load. This one here, it's a very small deflection, and this is deflection when I've got the mass added. So basically, we're assuming that the extra deflection is what this model takes into account. So that might be a sort of like a first approximation, probably. Anyway, what we can do is we can say, well, how good is that approximation? Well, rather than theorize, let's go and measure it and see. And what you can see is that deflection versus length cubed is a really straight line. Not entirely straight, of course. And we've got something called a product moment correlation coefficient, which is the R squared value. Actually, R is what that is, and the square of it's the sort of unsigned version. And that, if that's 1, that means all the data points will lie on that straight line of best fit from the origin. So this is a very, very good, very strong correlation. So what we can say by this is because the R squared value is very good, it means our model is well correlated to reality. That doesn't mean we've proven the model. We are not allowed to prove anything in physics. That may sound depressing, but I think Professor Fritjof Feynman says, you know, like, physics is the calculus of doubt. I may not be correct about that, but that is a if that's Thomas Kuhn or something like this. But basically, you know, we're in the effort of trying to disprove things. You know, you can't prove anything in physics. You can only show inference or correlation. But for most of the things, think how much of our world that we can control. You know, this conversation, I'm relatively confident that we are. You know, we understand the movement of electrons, so we can set up the communication system between you and I. You know, so we can predict the world with startling precision for a certain number of things. And this is one of them. You know, to a great degree of correlation, we can predict the deflection of a cantilever based on the length of its cantilever and the load at the end. We can do more than that as well, because the gradient of that graph is mg over Young's modulus Wt cubed. So from the gradient, which is 0.3093, that's in SI units, I can calculate y. And I'm just going to show you the calculation here. So here we go. So if we plug it into the equation, all right, rearrange it and stick in all the numbers, what we get is about 4.9 gigapascals. And according to, I think it's engineering, toolbox.com, a very good website for the mechanical properties of timber, between 3 and 10 gigapascals is the Young's modulus of wood. So that's kind of within that range. That sounds reasonable to me. So there we go. That's an example of a really nice experiment. We are doing. I do yoga. I like the idea of flow being a bit of sort of language which I'm happy with. And this is a physics flow. You know, you've got it's a real experiment and idealization of the real world. A cantilever which you set up. We've measured all the parameters. We've got a model for how the deflection works. Let's just have the right picture for that. For the deflection. And then we've measured it. And then we can ask ourselves, well, you know, how well correlated is our model with reality? And we can actually answer that and then work out other things. Given it's correlated, what's this other parameter of wood that we can measure? So then we could use this as a model for larger structures and maybe all sorts of engineering things. All right. So there we go. That's the kind of physics flow. And basically in rough handfuls, that's what we do all the time. Whereas it's a quick 10-minute experiment in the lab, maybe an hour experiment in this case, or a 3-year PhD or a multi-million pound or multi-billion pound mission to Mars or something like this. It's the same concept. Okay, we're going to talk about a few more examples, but do we have any questions in the chat so far about this?
No, all good so far.
All good, excellent. Right, so I'll go back to our presentation. I think most of the things, I think we might be hopping around a little bit today, but I've got a kind of flow related to the pendulum, which we can have a little look at. So here's the pendulum. And so if you can, you can make a theoretical model. There are some times where you may not really know what the parameters are. Although I think in physics, it's always a good idea to try and figure out what the key parameters are going to be and try to make some predictions before you start experimenting. And it kind of lets you sort of know what the territory is you're trying to map out. But, that may not always be the case. But of course, in terms of a pendulum, this is a well-known example. So it's worth just going through this because this is all kind of A-level stuff. Here's our pendulum bob, and I've got my sort of I've got a kind of arc here. That's the speed of the pendulum. Of course, that's an instant in time. I'm actually tracing out a sort of a sort of vertical circle. I've got the height of my bob from the ground. M is the mass of the pendulum, L is the length of the pendulum, and theta is my angle. G is the strength of gravity. So in drawing your model, what we're kind of doing is saying, what are my input parameters of this system? So think in terms of code. What are my inputs? What am I doing to those inputs? What are my outputs? And I think that's a really good way of kind of working your way through a problem. This is very much the essence of science by simulation, very much the essence of this course, and indeed the challenge, which we will release in a few weeks. So Newton's second law, we can say mass times acceleration. Now, if that notation is unfamiliar to some of you, theta double dot is the rate of change of angle, the angular acceleration. All right, so because length times angle is arc length, the acceleration is going to be sort of the length times the angular acceleration, because our length of our pendulum is going to be constant. So that's how we can write the acceleration tangentially. And if we sort of project the various forces, so mg sine theta is going to be the tangential components of the weight. All right, so I hope you sort of see that. I'd probably read a better diagram than this, actually. If you extend that angle, you can see that the sort of weight sort of times the sine of the angle is sort of opposing this velocity vector. And if you use a small angle approximation, sine theta is approximately theta. So there's another good thing. You can say, well, you know, this pendulum isn't really going to work for this model if my angle is too much larger than, say, 1 radian. And then if you sort of recognize, that's what we call the equation of simple harmonic motion, which I'm going to be teaching my my 4th years fairly soon. Some of you may have seen that before. And basically, simple harmonic motion says that the angular acceleration, or any form of acceleration, is minus times something times the displacement itself. In this case, the displacements are angle. And the thing that's in front of it is 2 pi over the period of sinusoidal oscillations squared. So this is going to oscillate, all right, with a period t. And if you compare that to what you get from Newton's law, you can work out the period. In this case, it's 2 pi root L on g, which is the period of my pendulum. So that's now something that we can test. So our model of a pendulum is, if we linearize it, that if we plot gt squared versus 4 pi squared L, we should get a straight line graph. Okay, so there we go. Challenge is released. Won't be today, I'm afraid, but will be in a few weeks. So the idea is that we've got a model, we've linearized it, and now we can try and test this. So there we are. So here's the kind of plot as you go system for the pendulum. All right, and I've got a straight line graph. If I've plotted, so this is a tiny bit small at the corner, but gt squared, I think I've got t squared at the bottom here. So there we go. So you plot t squared, let's call that x, and 4 pi squared times the length. All right, the gradient is actually the thing we're interested in, which is g, the strength of gravity. All right, so another thing is that we don't have to be totally wed. I might be saying something outrageous here that are, you know, this independent and dependent variable idea. Well, I think when you linearize it and plot the axes such that your gradient is something useful. All right, it doesn't want to be like 1 over g or root g or g times some random factor. What you want is the gradient to be the thing that you're interested in. So work up your axes. In this case, x is the period squared, and the y-axis is 4 pi squared L. That's the rearrangement of this equation here, which is how the period varies with the length and strength of gravity. And we also notice that it's nothing to do with the mass. So there we go. And in my case, I got 9.68, so not quite as high as the actual strength of gravity, but as it turns out, measuring g is actually quite difficult, believe it or not. Anyway, so there we go. There's a nice little example of this. And something I might also want to do once I've got this is to underlay my data with a model curve. So the finding g bit, the linearized form, is that's really the analysis. But we want to kind of go back to the original model and sort of just make sure it all makes sense. So once I've figured out what my model is, this one, I'd like to put a smooth curve underneath our data points. So I always sort of, it's my practice certainly to have a model curve as well. And I don't have data points there. I have that a much finer in sort of, gap. So I've got every, 1 centimeter, whereas my measurements every sort of 15, what have I got? So every 20 centimeters or so. All right. So there we go. So we're underlaying our data with a model. All right. And the parameters of the model, in this case, we know what G is, but we might, in the previous case of the cantilever, we don't know what the Young's modulus is. And we'll have to sort of find that information from the analysis. So we could all do that on Excel, but we don't have to. Could we maybe make a computer program to do this? So here we go. This is the same thing I've done in MATLAB, which is my favorite language. Other languages are available. And so this is how you would run it. So this is the sort of MATLAB command window. And I've got a little bit of code which I'm going to run here. And so this is what it looks like inside. And if you've never seen anything like this before, the sort of commentary all right, which has the sort of percentage sign, describe what is happening. So when I'm writing code, I always start with this first. So what am I going to do? I'm going to load the raw data from Excel. I'm going to determine some averages and errors, and I'm going to plot xt squared versus 4 pi squared L. This is what I'm going to do. And then I'm going to do a line of best fit, and then I'm going to make a picture. So I've said it's a text file. This means commentary, vital for humans, ignored by machines. So, but this is how I recommend you code stuff up. All right, so here we go. So this is happens to be the code in MATLAB. So there's an XLS read function. Every language will have its own sort of interface to things like Excel or CSV files, a sort of more common format of spreadsheets. And what it's doing is it's giving me some arrays, some matrices, which basically correspond to these. And then I might work out some averages of my times. I probably don't want to read that, but the only information you can get is that this is my plot routine. So I've got, I'm plotting length versus the model. I'm setting line widths, the colors of things, all that kind of stuff. All right. And what's nice is that you can get your formatting sorted out and then you can forget about it. So this comes directly out of this code. And you can see I've got a really nice looking graph here, and I've got all my error bars calculated. And I'm underlaying my data. So my error bars in time are very, very small. You can't see them, but in length, they're just about visible. And you can see that my data is underlaid very nicely with my model curve. So this is the line of best fit. And I think I've got a slightly better picture of this. Here we go. So I can actually work out an error in my line of best fit. I've got some analysis of this in this presentation. I don't think I really want to get into that so much today, unless some of you want to have a little dive into that a bit later. But if you're interested in the mathematical details of how to work out a line of best fit, do download this presentation or have a look on the Eclecticon. I can certainly show you some links of how you can derive that and make your own recipe. It's quite a satisfying thing to do. But so what you can do is your lines of best and worst fit, you can actually kind of work out using some statistics on this graph. They're actually very, very close to this data because it's so well correlated and the errors are so small. So there we go. So I've plotted the line of best fit and it's about 0.994. So in this case, I've plotted the period that we measured versus the period we predict. So if I don't want to actually measure something like G that I did in this one, all right, so my gradient is G. Alternatively, I might say, well, I know what G is. Let's just see if my prediction matches my model. And in this particular case, I think this is the better thing to do. So the period for my model, 2 pi root L on G, is my y-axis. And that's given my measured values of L. And my x-axis is what the period actually is that I measured. And if you plot the two together, we should find a graph which is y equals x. And so from the line of best fit, it's 0.994 plus or minus something rather small. And the R value, remember R squared is what Excel gives, the R value is very close to 1. So this is a very good correlation. So there we go. As I said, if you don't need to find parameters in the data, simply compare model versus measurement is a really nice thing to do. So ask yourself, we always want to have a straight line graph. Can I rearrange my data, my model, so I get this? Do I want to measure the gradient or the intercept? Does that give me something interesting? If not, if we know all the parameters, let's just plot model versus prediction. Okay, so there we go. I think that's probably enough for this one. So I think do we have any questions on what we've seen so far?
No, not right now.
Okay, so I'm just going to bounce out of this for the moment, and we'll kind of have a look at a few other examples. So this is something which I was doing in Shanghai last year for BPHO for some year 10s, some fantastic year 10s in Shanghai, and we were looking at slinkies. And we've done this in a variety of guises with the Olympiad. And this is a really nice experiment that you can all do at home. So I'm just going to sort of describe how this goes. And the model for this is also lovely as well. So let's make that a bit bigger. So let me just show you where you can get this. Hopefully I can run this one. So hopefully that will get there. Okay, so this is my website. And if you go to physics and you go to, I think it's under courses, computational challenge. Oh, yeah, so that's where you can get all the bits for what we're talking about. So today's models, experiments, so slinkies, etc. If you click on that link, it's actually a zip file. And in that zip file, you'll get all this data. So Slinky Physics will appear. All right, if you want to have a little look at that. It is in other places as well. So I think it's under maybe experiments. Nope, it's not under there. It's under, I think, mechanics potentially. No, it's not under there. Maybe it's under waves and optics. Yes, Slinky Physics. There we go. So we're doing oscillations. And you can also access all this stuff for free as well. Let's just make sure I don't close your window. Are we still recording? I think we are. So here we go. So this is all you need. So we did this first during the COVID times, or just after that, online. So I had loads of people. So all you need is get a very cheap Slinky. That's the Rainbow Magic Spring Slinky. I think it's cost about £1. And you'll need a sort of a tape measure as well, and a desk. And I've got a very large book which sort of weights it down. So there we go. So that's a copy of Gravitation by Meissner and Thorne, which is the heaviest book I have. A very weighty tome in every sense of the word. And this is it. So I've got a stopwatch. And what we're going to do is we're going to record the number, or count the number of coils that we expose beneath my desk or beneath my clamp here, and then measure the length of my vertically hung Slinky. So you want to choose your Slinky so it doesn't hit the floor. So this is why this Magic Spring Slinky is quite nice. The really big ones, you might find it just extends to the floor and it's a bit too unwieldy. So a kind of cheap Slinky is actually rather better in this case. So there we go. It's about 38 coils, something like this. And so there's two things you're going to do. Is you're going to measure the length of your vertically hung Slinky, all right, versus the number of coils you expose. So I can put more coils under the book to reduce that. And then I'm going to actually sort of pull the Slinky down and measure its oscillations. And they're rather cool because it's not like a sort of Hookean spring, all right, is that the gaps between the coils are sort of less as you go down, all right? So that at the top, you've got more Slinky pulling down. So it's the spring itself is providing the weight. So as it oscillates, it's a kind of like a pupa, like a kind of, sort of like a centipede, it's sort of a worm that's moving around. It's quite pretty to look at. But nonetheless, we can work out the period. So what are we going to do? We're going to need a spreadsheet for measuring period and number of coils and length. And we want some sort of model that allows us to analyze these things. So this is what we'll do. So I'm just going to give you some examples of what we'll measure. So this is the static experiment. So there we go, 29.1 centimeters is this measurement for 25 coils. And there we go. So you get your eye nice and low, so you get fit. And so you can, make sure there's no parallax error, and you can do it to a millimeter or so. And there we go. And that's the top of our measurement. All right. So what you can do is you can make smaller ones by sandwiching your Slinky underneath your book. And the period is quite small for those. And there we go. So this is basically what we're going to do. Now, if I sort of make that nice and big so you can kind of see what we're doing. Hopefully that's not too... Is that, so can I just say, are the numbers just about readable? Do I need to make them bigger?
Just about. If you could make them slightly bigger.
I'll make them slightly. I can scroll around. So there we go. So this is the sort of thing you'd want to select. So once you've set your experiment up, you want to then, right, before I take some measurements, there's no delay here. It's not like a sort of radioactive source which is going to diminish. It's not expensive. So you've got your kit set up. Right, what am I going to measure? How am I going to take data? So I would set up a spreadsheet and a table, and my pilot experiment might suggest, well, how many coils do I want to expose? It's not going to be one, and I don't want to do loads of measurements. So I know, what have we got, about 10 or 12 measurements here, something like that. 1, 2, 3, 4, 5, 6, 7, 8. In fact, 14 measurements. So between 10 and 20 measurements, I think is good enough for a kind of school laboratory kind of thing. And so I sort of, with my pilot experiment, I've sort of deemed that, say, between 11 and 37 coils, something like that, is a good idea. So I'd basically play around with your kit and just sort of find out, you know, the range of sort of what's happened, where the action is. So there we go. So this is my slinky length that I've measured. So I'm measuring these ones versus the number of coils. And then I'm going to do some repeats. All right. So I'm going to, using my stopwatch, find out what the period is. And obviously one period is going to be too quick to measure. So I'm going to measure 10 of them. And that's not too unwieldy. So for the maximum number of coils, that's under 15 seconds. So this isn't too tedious to do. And so then my spreadsheet will automatically divide to work out the average period and divide by 10. And there we go. And this is going to be the standard deviation, which is the std function or stdev function in Excel. So basically my answer for period in this case, so let's go for the n equals 37, is 1.238 seconds plus or minus 0.04. And that will be your measurements. All right. So don't go, oh no, what do I do about errors? You want to build in your calculation of errors as you go, and then you'll transform your life from being a sort of tedious thing to something which is really good fun. So this is the hybrid between human and machine. You know, get your computer to work out your sums for you. The human is setting things up so you can see visually what you're doing. And now what do I want? So it turns out that a good model of the length of your hung slinky is actually as the square, believe it or not, of the number of coils. Good, isn't it? So again, you don't want to have linear things. They're boring. We want this a square. All right. So there we go. And if we plot, so we don't know what the constant is. So if we want to do, what we want to do is a straight line graph of n squared versus versus, I like the emoji. It's just flown up on my screen. That's hilarious. So so we want to plot n squared versus the slinky length. All right, and see what the gradient of that is. So there we are. So my model is L is beta n squared. So if I plot L versus n squared, the gradient of that graph is going to give me beta. So what I want are actually 4 graphs here. So there we go. I've got length versus number of coils, which is the data I measure, L versus n squared. And we can see this is a pretty good straight line, all right, going from the origin. Excel doesn't go all the way to the origin. That's just what it does. It doesn't extrapolate. We've got a really good R squared value for this. And if you look at the line of best fit on Excel, if you tick all the options, you've got a nice, a nice product moment correlation coefficient. So once we've got these, all right, we can then work out a model, which is, okay, I think we've probably had enough emojis now. Thank you very much. And we can plot N versus L, all right, and we can underlay our data from here, okay? So, and that's the red code is based on what I've got under here. So what else can we do? Well, we can also look at the time of this, the period. Now, this actually is a linear thing, although actually we can go back to our pendulum and we might sort of suggest that the period of our slinky, it's a bit like a pendulum in some ways. So we might expect it to go to the square root of its length over the strength of gravity. So, and in fact, actually, that's not a bad model. But this parameter alpha isn't 2 pi. It's something else. I think it's the square root of 32 or something like this. But as L goes as n squared, that means that the period should be proportional to the number of coils. So we would predict the period of our slinky versus n to be a straight line. And indeed, that's what you see. So this is great. So we're measuring period and we're measuring length simultaneously. And as we do the experiment, these graphs will appear and we can kind of see whether our model is correct or not. And that's so much better than taking a load of random data, plotting it at some point where you've forgotten to do the experiment and then maybe you've made some errors. Or you've realized that you haven't captured where the action is. So, you know, spending a bit of time figuring out what you're going to measure, how you're going to take the data, how you're going to plot it is a really good idea. And then the good news is once you've done your experiment, you've got it written up pretty much, because if I zoom out a bit, that goes in a presentation. In fact, this is literally a screenshot from an Excel sheet where I took the data myself. So there we go. We've added a trend line. Now notice we've not got a y=mx plus c trend line here, because we're assuming there is no y-intercept. That's not always the case. I'm going to show you an example where the intercept is useful. But if there was a y-intercept, that means we've got some sort of systematic error. So in other words, maybe my stopwatch, I'm starting too late. But in this case, it's pretty well correlated. So there we go. So that's a nice little example. And here we go. That's just a sort of summary of all the graphs. So there we go. If you're interested where the L versus N squared comes from, I've got the derivation in this presentation. It's quite fun. It only requires, I think, A-level calculus is all you need. But it's not quite like Hooke's law. But we do have a conundrum, which I think Professor Chung explained to me, and I'm afraid I still don't understand it. So we can have another go when we're in Shanghai. But I still haven't quite convinced myself what that constant is and why. All right. So so that's an exercise to the reader to see if you can figure that out. But anyway, the point is doing the things experimentally. This is our encounter with reality. So, okay, so we've got a few minutes left. I'm going to give you one more example, and then we're going to have a look at rocketry again to finish off. So if we go back to our experiments, I think it's under here. Yeah, here we go. So I think it's actually, we'll go for this one. Yeah, this will be quite good. All right, so here's an experiment which is a very common one for A-level physics. In fact, we do, if you do the OCR boards, this is the one you'll probably do as a required practical, something like this. And the idea is you have a Geiger-Müller tube, a detector here, and you've got some sort of source. So this is going to be a gamma source, all right? And what we're going to do is in the space between the gamma source and the detector, you're going to put something like an absorber. And given its gamma rays, we're going to need something dense like lead for making a difference. And what we're looking at is a sort of half-life-like formula. Rather than half-life in time, for a source of decay, we've got distance. So this is a half thickness, all right, decay law. And so this is how you might set it up. So there we go. This is a pretty ancient counter. And the way you do it is, so this experiment, the way I did it was took a bit longer than a few minutes. So you count for 100 seconds, and then you can average. So this is our lead line box for our cobalt 60 gamma source. It's sort of a popular one in most schools. And then what you do is you put your absorbers between the detector and your source here. All right. And then we go to your forceps. So it's good practice not to get a radioactive source in your line of sight, because obviously the gamma rays will be passing through your body. Although it's to note the activity of our source is going to be very, very low. Basically, if I just sort of show you, this is our radioactive buckets, which we use for carrying sources. And I think probably the greatest danger here is actually the sort of poisoning from the lead. So if you're handling lead, please wash your hands afterwards and don't lick your fingers. Anyway, so what you do, I'm just going to scroll across. Here, there we are. That's the name of our source. That's 5 microcuries, not much. Now let's have a little look. So there we go. So what we're going to do is, here we go. Here's our data. So guess what? We've got another spreadsheet which we've set up in advance, and we've got the lead thickness. All right, we've got maybe 3 repeats. So A is my counts per 100 seconds. And then I can turn that to becquerels by dividing by 100. And I think in this particular case, I've also worked out a background as well. So this is without the source. So I've got about a background count of about 0.3 becquerel, something like this. So I can remove that from my count. It makes a very small difference, but perhaps actually when we're talking at the end here, we're sort of certainly into background here. So this is the average divided by 100 after sans background. Then I'm working out the standard deviation of those numbers, and then I can work out some error bars. So what I can plot is I can plot the count rate and the error bars here, and you can actually do that in Excel. It's a bit tedious, and I've got a little note in my Excel course. So if you look on sort of computing on the Eclecticon, you can sort of see how to do that. But if you do a Google search for in Excel, how do you do error bars? You can sort of follow the recipes. And I'm underlying this curve with a smooth exponential decay. So if I've got an exponential decay, I want to log the data. So this is going to be my analysis. So what I'm assuming is that my activity is exponentially related to the thickness of my lead. So in other words, a nice way of writing that is to say that my initial activity, in other words, no lead at all, divided by 2 to the power of the number of half thicknesses. So when x is equal to x half, I divide my activity by 2, etc., etc. So if I do the logs of this, if you sort of follow this down this way, I've got 2x over x half is a naught over a, log both sides and rearrange. And if I plot the log of my activity, I get the log of the initial activity minus log 2 over x half times my thickness. So if I plot, if I just make my graph nice and big, if I plot the log of my count rate versus my thickness, I should get a straight line graph. It's got a negative gradient, and the gradient is going to be log 2 over my half thickness. So if I measure the gradient, and it's the, if I take away the minus sign, that will then allow me to work out what my half thickness is. But I also get a y-intercept as well, 0.9069 in my case, and that will also tell me what my A naught is going to be. So, I mean, I could just sort of compare that to direct measurements as well, but allows me to kind of create a model. So in my case, that's what we've got. So it gives me an A naught of 2.477 and an X half of 12.33 millimeters, which is then what we can use to underlay our data. So there we go. So if you look at A naught, the 2.48 becquerels, slightly higher than the data point I measured here. But remember, this is a random phenomena. So that's quite acceptable that that's going to be sort of wiggling around where our data points are. So this graph is what you do for analysis, the linearized one, but we really want to plot the data versus the measurements as well and underlay our model. And that really gives you a sort of warm, fuzzy feeling that your model actually is linked to the data that you've measured. So there we go. I think we've done about 4 examples of looking at pretty much the same thing. And pretty much all of them are Excel, although, of course, you could do the lot in MATLAB should you wish. So I think what I'll do is I'll finish off showing you what we're doing right now. Well, not literally right now, but with our rocket project. I've got a little sort of, we've seen the launch. Let's look at another launch. Here we go. I think this is, we'll see this one again. This is the parachute test, which didn't quite work. There we go. So the whole valve fails at about 4 atmospheres. All right. And well, in this case, it sort of went about 10 meters in the air. And the nose cone detaches, but sadly the parachute does not. There we go. Crash. Bosh. There we go. A detachment of the parachute at the end. What we're doing is this is currently my analysis. You can sort of see. So what can we see here? We can see some green text. So this is what's going on, and I've got 2 bits of code. I've got one which ingests the data. So these sheet names, if I load up my Excel sheet, here we go. So this is thrust versus time for my data logger for different initial masses of water. I think I've got a graph maybe for one of these. There we go. That's force versus time. I need to double this because of my seesaw effect. And then I've just got force versus time for all of these. And you can see there's quite a lot of data points in here. So 18,762 to be precise. Because we're recording at 1,000 data points a second. All right. So this is not something you could write down yourself. So this is a lot of data. We want a computer to process this. So what I do is I run this little thing in a loop, and I'm going to determine all sorts of stuff. So let's including things like lines of best fit. So let's just sort of run this. So that's the ingest, and I'm going to go and plot it. So if I plot the if I show you the sort of timing on this one, if I run this expression, it's loading in the data, and I've got a bit of feedback in the corner which tells me how it's getting on. All right, it's a little bit slow because it's a big Excel sheet, and then once it's got to the end, it will give me a nice sense that it's completed. Let's just finish it off. There we go, and it's going to plot a whole bunch of graphs. So naughtily, I've not got an axis on this, naughty me. That's thrust. That's actually related to the logarithm of thrust versus time. So what I'm looking at is an exponential decay model of thrust versus time, a kind of half-life, a bit like we just saw with the gamma photons. I've got oodles of graphs here. So this is for each run. So you can see that we've got a relatively good correlation. There's lots of wiggles earlier on, but it's not too bad. So from there, so if I load up rocket data, this is what now it's imported into MATLAB, and I've got all sorts of things like I've got my sort of maximum thrust, all sorts of stuff that I can then use. So if I run this program here, I can then ingest that. If I just get rid of everything so you can see, I should just close all the windows. If I then run my plot routine, and this is basically reading in my rocket data and then plotting it, and all these sort of like purple things are commands about style, like what are the labels, what are they called, what's the font size, all that kind of stuff. So if I run this, it'll do some plots and make some pictures. So if I explore those, so what we've got, so this is literally just demonstrated. It's this. I've got all the different initial volumes of water, and I'm plotting thrust versus time. And what I've had to do is I've had to cut the data around where the action is. So it records for ages, and then suddenly it will go. So I've aligned those, so it's all, so everything starts. The clock starts when I have my maximum, and then I can compare everything together. It's quite busy. We can see it has a maximum of about 110 newtons. There's a bit of wiggle going on here. The ones with 0 grams of water, that happens quite quickly. Whereas as we add more water, it takes a bit more time for the water to leak out. But otherwise, it's quite hard to see. So the next graph is I'm plotting the half-life of thrust versus time, an exponential model. And this is completely new data. We've not only just started analyzing this, but it's possible that there's a moderate correlation between the time it takes for water to be ejected, an exponential model. So my half-life seems to be related to the mass of the water that we've ejected. And my initial measurement seems to think it's about 0.3 times the mass of the water is the half-life in seconds. All right, so that's something that we can then experience. We've also got a kind of a systematic error here. We maybe that should be 0, but we can have a think. But the maximum thrust versus initial water mass is all over the place. So that's really badly correlated. So whether we've got an exponential model for thrust versus time, the jury's out, but we could at least make a start of thinking about that. So there we go. That's taken you home through a little journey, a little explorer of experimental work. We looked at the cantilever, radioactive decay, slinkies, bit of rocketry, pendulums. We are trying to do an experiment. We are setting up a spreadsheet, or in this case, a data logging system to record the data and think how we're going to analyze and present it. And almost in all situations, we're trying to think about, can we do a line of best fit, right, to our model so we can assess correlation. I haven't put the R-squared value on this, so I'm going to leave this as a surprise for my students. But it's not too bad. Then you can assess the efficacy of your model quantitatively. And then if you've got a correlated model, then you can start to work out parameters, in this case, like the half thickness, in case the slinkies, the beta value, etc., etc. All right. So this is the direct counter reality. That is what physics is really all about, I think. Hope that was fun, and we'll see you all next week. I see the emojis have appeared again. Thank you very much. There we go. Oh, sea of emojis, marvelous. I've got this little video. There we are. A little picture of our rocket. There we are. There's our rocket rig.